Okay, so let's talk a little bit about how our nomenclature rules fit in with assigning stereochemistry at chiral centers. So the configuration of the chiral center, so R versus S, is indicated at the beginning of the name, italicized, surrounded by parentheses. So for example, this molecule would be R2-butanol. Just to show everyone why this molecule is R2-butanol, if we assign priority 1, 2, 3, and from our priority groups, we're going clockwise. Ergo has the R configuration. Oh, let's check that really quickly. Yep, everything looks good. Okay, now let's take a look at this next example, and this is a common error I often see students make, and that's why I have this example in the notes. So if a molecule contains multiple chiral centers, the locant number of each chiral center is indicated before the configuration. So I'd like you to compare the structure on the left to the following structure that I'm going to generate on the right. And I'd like you to tell me, just really quickly, does anyone notice a problem with this structure on the left? So sometimes students, when they see dash and wedge, they immediately think chiral center. But we first have 2R, okay, for our 2-butanol. So we're saying this alcohol has an R configuration. And then 3S. So we're saying that this center is an S center. Would someone like to comment on this second center? Is this second center a genuine chiral center? Is this second center a genuine chiral center? Exactly right. So we need to strike that out. So the correct name for this structure would just be 2R, 3-methyl, 2-butanol. And the really critical thing that I want you to take away from this example is only indicate the configurations of chiral centers. So with one quick fix, if we add a carbon, the name for this, so the configuration at our alcohol is still R, and the configuration at this second carbon, which is now a chiral center, is S. So this would be 2R, 3S. So this is position 2, this is position 3. So we put the locant followed by the configuration, comma, locant number, configuration, and then we name the molecule as normal. So this would be 3-methyl 2, and instead of butanol, it would be pentanol. Does everyone understand why we're naming the why carbon 3 is chiral in this structure on the right? Does everyone understand why carbon 3 is chiral on the structure on the right, and ergo why we have to provide the configuration in its name? Does that make sense to everyone? So just as a review, for a chiral center, so a chiral center, there are two criteria. One, we have 4 different substituents. And 2, there's no axis of symmetry. So if we look at the structure on the left, we have a methyl group and a methyl group. So we have 2 identical substituents, and as a result, this center has a plane of symmetry. So it's not a chiral center. Does that make sense? Okay. So the one thing I want you to highlight is when you're naming molecules with chiral centers, always just make sure to stop and verify that the centers which you're assigning are genuine chiral centers. Then you name the carbon number, so this is our locant number, followed by the configuration in the front, and then you name the molecule as normal. And then this is just the name of the molecule exactly as we've done before. So the only thing new with the introduction of chirality and chiral centers with different configurations, the reason why it's pentanol in the second example is so that way we have an ethyl group and a methyl group. And because the substituents are different, now carbon number 3 is chiral. So this is just showing how when naming structures need to pay special attention and always double check that your chiral centers that you're naming are genuine chiral centers. Does that make sense? And it doesn't take a lot in order for you to go from a chiral center to a genuine chiral center with no axis of symmetry. It's literally just the addition of one carbon. So just be careful when you're selecting the name for molecules that you don't get ahead of yourself and skip the part where you just verify that all the chiral centers are actually chiral centers. Okay, we'll talk more about naming molecules as we approach and we handle different functional groups. For now, what we're going to address next is a critical distinction between different types of stereoisomers. So enantiomers are a very specific definition. They're a pair of molecules that are non-superimposable mirror images. Remember our example of the hands. You can't lay them on top of each other. They're non-superimposable mirror images. The way that I like to remember chiral centers, since we're really good at assigning RS, is that enantiomers have the opposite configuration at every chiral center stereocenter. Okay. So boxed. So in these boxes are pairs of enantiomers. And as we notice, if we look at the configuration at each of our stereocenters, if we compare our two enantiomers, are the configurations the same or the exact opposite? Are the configurations the same or the exact opposite if we compare the two compounds in the box? And I see people already typing in the chat opposite. Exactly right. You can identify enantiomers by looking at each stereocenter and verifying that the configuration at each stereocenter is the exact opposite in the enantiomer. So for example, we go from RR to SS. Okay. Now, diastereoisomers are a set of two molecules that have the same bond connectivity, but a different configuration in 3D shape at one or more chiral centers. A key thing, these molecules are not mirror images. So we're only changing the configuration at some of our chiral centers. So for example, in these curved boxes are diastereomers. So does everyone notice how we go from S to R? However, the alcohol stereocenter stays R. So for diastereomers, the way that I like to remember it is that one or more, but not all stereocenters are flipped. Does that make sense to everyone? Do these definitions make sense? Does anyone have any questions so far? I see some people typing yes in the chat. So let's keep going. We'll notice some gaps once we start to apply this, but for now, these are just the definitions that we're working off of. Now, there's a nice little rule to help limit the amount of structures you have to draw. Since when I tell you to draw all diastereomers, we can limit the amount of stereoisomers we have to draw. The number of stereoisomers for a molecule is equal to 2 to the n, where n is the number of chiral centers. So let's apply this rule, and let's apply this to the following example. So we're asked to draw all possible stereoisomers, and we're asked to label each set of enantiomers and diastereomers for the following molecule. So first things first, before we even start drawing out chiral centers, let's just label some carbons, 1, 2, 3, 4, and let's just identify really quickly our chiral carbons. So which carbons are chiral? And I'll even draw out the hydrogens just to help everyone along. Which carbons are chiral in the following molecule? And don't be shy to type in the chat or unmute and voice your input. So for chiral carbons, remember rule number 1, we have 4 different substituents. And there's no axis of symmetry. And most importantly, in general, chiral carbons are sp3 hybridized. So for those who answered 2 and 3, you're exactly right. Okay, so in terms of our total stereoisomers, it's 2 to the n. So n is equal to 2 because we have 2 chiral carbons. So we're going to take 2 squared, and that gives us 4. So you know at maximum, we will have to draw a total of 4 structures. Okay, so let's just go with that. So I'm just going to start by drawing the wedge. I don't actually have to assign the configuration in any of my centers. The trick is if we want to draw an enantiomer. So let's suppose we want to draw a pair of enantiomers. Then I just have to draw the mirror image of this molecule. And by far the easiest mirror image to draw, is just to change all my wedges into dashes. Here we go. So we have our first pair of enantiomers. We've inverted and we've flipped the configuration at every single chiral center. Does that make sense? Can everyone see as to why these 2 molecules are enantiomers, non-superimposable mirror images? Okay, so let's try now to draw a pair of diastereomers. So let's draw a pair of diastereoisomers. Okay, so we're just going to flip one of our centers. So I'm going to pick to flip center number 2 if we're using our carbon numbering. We'll just flip the configuration at that center. It's completely arbitrary, but nonetheless, it can be quite instructive. Okay, so we're just going to change the wedge to a dash. And although it may seem like we're making relatively minor modifications to these molecules, changing the stereochemistry can vastly change the potential cost to generate that molecule, and it could definitely change its reactivity. Okay, so we have diastereoisomers here because we've just inverted one of our centers. And now to finish things off, we're going to draw another pair of enantiomers. So I like to call this the square method. It's really good when you have two chiral centers and it can be expanded for more than two chiral centers. So for our pair of enantiomers, so all I'm going to do is I'm going to take each of my centers and I'm just going to invert them. So for my pair of enantiomers, I'm going to convert all my dashes to wedges and all my wedges to dashes. And now we have our second pair of enantiomers. Okay, now I'm going to put some numbers. So 1, 2, 3, 4. So which pair of molecules are diastereoisomers? Which pair of molecules are diastereoisomers that I have not yet labeled? Besides 1 and 3. But that's very good. That's very good. You're on the right track. Let's try to find another pair of molecules. Another pair of molecules that are diastereomers. I see a lot of people typing 2 and 4. That's exactly right. So 2 and 4 are diastereoisomers, which we often abbreviate as diastereomers. Why? We have just inverted one of our chiral centers. Does that make sense to everyone? Does this square method make sense to everyone? Essentially, I draw a random molecule, whatever configuration I want. Then 2 and 3, yes, that's exactly, yes. 2 and 3 are also a pair, exactly right. Good. Just like also 1 and 4 are a pair, because we've in effect inverted one of our stereocenters. Exactly right. Essentially, your horizontal connections are enantiomers, your vertical and cross connections are diastereomers. Is everyone comfortable with this example? Would everyone be comfortable working on an example in small groups together? Okay, so let's first talk about one exception. Let's first talk about one exception and let's talk about a procedural method. If you need to assign compounds as enantiomers or diastereomers. So how do we do that? First things first, you check for symmetry. You check for an axis of symmetry because that can immediately raise some red flags. We'll talk about that in a moment. You can then assign the configuration at each chiral center. So if I just give you a pair of molecules, you're going to need to assign the configuration often. If the two molecules are enantiomers, if they're enantiomers, non-superimposable mirror images, the configuration will be flipped at every chiral center. Okay, so we've already seen that. So R goes to S, S goes to R. So these two pairs of molecules are enantiomers. And of course, where are we getting these R and S assignments from? We build the model and we use the configuration assignment rules that we talked about in previous lecture. Okay. So if the molecules are diastereoisomers, the configuration will be flipped at one or more, but not all of our chiral centers. So for example, S gets flipped to R, but the alcohol stereocenter stays the same. Just putting into words the rules that we've been slowly building into this in this section. Okay. So with that refresher in mind for the rules, let's take a look at just a pair of molecules. Let's just take a look at a pair of molecules and let's determine whether they're enantiomers or diastereoisomers. So since this is a new type of problem compared to just the brute force drawing all the stereoisomers, I'm going to do this one, and I'm going to ask for your input periodically, okay? So first and foremost, we need to make a model. And even if your model kit doesn't necessarily have all of the pieces, the more pieces you have, the more complete picture you have, and the less you have to start swapping out all of your carbons. So I'm going to make a model, and I'm just going to start with one of the structures. Let's start with the structure on the left. You don't have to do all of them, and that's the beauty. So let's start just by making a model of the structure on the left and assigning the configuration at each center in the structure on the left. And give me just one moment to put that together. And you may say, why are we looking at molecules that are so large? Well, most of the molecules that you'll encounter in biology aren't exactly small molecules by any stretch. So you want to make sure that you're able to apply these methods even to relatively complicated, quote unquote, complicated systems. I'm just testing this really quickly because the camera inverts. We're just making our model right now. And again, we're making a model of the structure on the left. Why do we pick the structure on the left? It's completely arbitrary. Almost. You have to really sweat the details on this. Otherwise, you'll end up with a structure that looks a little off. Okay, perfect. So here is the molecule as drawn and as depicted for the structure on the left, okay? So let's just do an observational check. So this alcohol group, is it pointing towards you or away from you? Is it pointing towards us or away from us? This alcohol. Away, okay, so it has the dash, so we've checked that off. Okay, is this alkyl group pointing towards you or away from you? What's closer, the hydrogen or the alkyl group? Away as well, okay, perfect. Is our alcohol, so if we think about our alcohol, is our alcohol, oops, let's see, oh, the center needs to be flipped. This is why we do a check. Okay, so now let's pay attention to our alcohol now. So we've drawn our alkyl chain in the same configuration, We need one more carbon on this. Let's get that fixed. Okay. Perfect. So our alkyl chain is depicted in the exact same way as the model. And now is our alcohol pointing towards us or away from us? Towards. Okay, perfect. So we've checked all the boxes. Okay, now let's start with our first stereocenter. So currently for our first stereocenter, our hydrogen is pointing towards us. So let's rotate this molecule so the hydrogen is in the back. Let's rotate this molecule so the hydrogen's in the back. And now all we're going to do is we're going to draw this stereocenter with the hydrogen in the back exactly as we see it. Okay, so let's draw what we see. So we have our alcohol pointing towards us. We have our hydrogen pointing away from us. Our chain with the alkyl group is on the left-hand side, while the rest of our ring is on the right-hand side. Okay, perfect. So we have center 1 established. Let's continue to take a look at this structure. Let's continue to take a look at this flipped structure, as we've also solved some of our problems for our adjacent stereocenter. So just as a refresher, we started off for our alkyl chain now. Now we're going to focus on our alkyl chain. Looking at the chiral carbon, is the hydrogen on that chiral carbon for our alkyl chain pointing towards or away from us? Is this hydrogen pointing towards or away from us? Towards, right? Okay. And just like before, hydrogen is a low priority group, so we're going to put it in the back. So we're going to take our entire model kit or our chiral center, and we're just going to flip it 180 degrees. Okay. So now our hydrogen's in the back, and now we just draw what we see. And we already have most of our picture right here. The only critical thing that I want you to pay attention to, that I want you to really focus on, is this idea that at this center right here, is our alkyl group now pointing towards or away from us? Is our alkyl group now pointing towards or away from us? Towards, right? So we'd give it a wedge. Okay, perfect. So let's now assign our priority numbers. Let's assign priority numbers. So starting off, I'm going to draw just the bare bones basic components of chiral center number 1. So we have our OH pointing out of the page, our hydrogen going into the page. We have this alkyl chain and the rest of our ring, okay? So let's focus only on center number 1, and let's assign priority groups. So what's our highest priority group on chiral center 1? What's our highest priority group on chiral center 1? And don't be shy to type in the chat. I see a lot of people typing the alcohol. That's correct. Alcohol is priority 1. The hydrogen's priority 4. And now let's compare B and C. Which substituent is higher priority? Substituent B or substituent C? Well, let's look. If we do a direct comparison, then it's a tie. But if we look at the substituents attached to B, so attached to B, we have 3 carbons and a hydrogen. Attached to C, we have 2 carbons and 2 hydrogens. So B wins out with priority number 2, and C gets priority 3. We now draw clockwise versus counterclockwise. So counting from 1 to 3, we draw our arrow. And are we going clockwise or counterclockwise? Do we have an R or S configuration? Counterclockwise and S. That's exactly right. Okay, so let's just assign that center. Now, we're doing this the long way for now, but there's a trick. There's a trick to do this faster, okay? So bear with me for this. This is also serving as a nice little review. Okay, let's now focus on our next stereocenter. So I'm going to draw out the basic components of that stereocenter. Okay, so focusing now on our second stereocenter, let's identify our highest priority group. So what's our highest priority group attached to our second stereocenter? So A, B, C. What's our highest priority group? A, B, or C? And don't be shy to type in the chat. I just want to get a few responses before I chime in. See a lot of people typing A, that's exactly right. That carbon is directly attached to an alcohol. And that oxygen wins out. So A will get priority 1, B gets priority number 2, and C gets the short end of the stick with priority 3. So now if we draw our arrow going from 1 to 3, are we going clockwise or counterclockwise? Are we going clockwise or counterclockwise? Do we have an R or S configuration at that center? So counterclockwise, ergo we have an S configuration. So let's put that up here. Okay, let's do one more. Let's do our last substituent, okay? So here we go. Here's our current depiction of our alcohol. Right here. Is the hydrogen in the back? Is the hydrogen in the back? Okay. And just to demonstrate this idea that you only need to know the pieces to rotate your molecule, if I just had a little bit of my model kit, I'd just take a look at this piece and I'd study it as this piece. But since I have more carbon atoms, I'm just going to use this whole molecule. So since the hydrogen's already in the back, I just draw my molecule as I see it. So I just draw my molecule as is, as it's originally drawn. Okay, so we have our molecule exactly as originally drawn. Now let's assign priority. So A, B, C. What's our highest priority group? A, B, or C? What's our highest priority group? B. Okay, yep, that's exactly right. An alcohol, an oxygen wins out over a carbon. What's our next highest priority? A. Yep, that's exactly right. And then C gets priority 3. So if we draw our arrow, okay, do we have an R or S stereocenter? Are we going clockwise or counterclockwise? I see a lot of people typing R. That's exactly what? Exactly right. Okay, so clockwise R. So let's fill that in here. Okay, now this was review, but what we can do, instead of manually solving the structure on the right, we can think, if we change from a dash to a wedge and our structure is drawn exactly the same, we need to make sure our skeleton is drawn exactly the same. Then when we go from a dash to a wedge, what would be the configuration at the indicated center? What would be the configuration for that alcohol? Instead of S, it would be R, exactly right. But this only works, this is only valid if the skeletons are drawn exactly the same, okay? So just really want to make sure you have that point solid. if you wanted, we can even in fact manually assign this center just to prove that. You know, there's no point in trusting that what I say will work 100% of the time. So let's manually use our from scratch method just to verify that this shortcut works. So the alcohol is 1, this adjacent species is 2, the species on the left is 3. We draw our arrow and lo and behold, we do predict it would have an R configuration. Perfect. Okay. So by the same token, if we change from a dash to a wedge for our second stereocenter, what configuration would we expect to see? R, exactly right. Finally, has anything changed for our third chiral center? Has anything really changed for our third chiral center? Has anything changed for this center here? No. So what's its configuration? What is its configuration? R, exactly right. So if we compare all of our stereocenters, have we changed all of our stereocenters? Have we flipped all of our stereocenters? Yes or no? No. What do we call it when we only invert one or more, but not all of our stereocenters? What do we call that? Is that an enantiomer or a diastereoisomer? Yes, that's exactly right. They are diastereoisomers. So we'll just write that they are diastereoisomers. Now you may say, why did we go through the trouble of manually assigning all the configurations? Well, because in later problems, you're going to see the skeletons drawn in different ways. And your goal when you compare molecules is to make sure that their skeletons are drawn in exactly the same way. So that way you can directly compare your stereocenters with no issues. We'll illustrate this with an example. I always want to remind you that as a last ditch, if you're stuck rotating the molecule, you can just start assigning each of the stereocenters and then comparing their configurations. That's a perfectly valid method. And that's why I always want to develop and train that skill. Okay. So to show you an example where two molecules may look very similar, but they're drawn in slightly different ways, let's try to compare the following set of molecules, and I'd like you to tell me whether this pair of compounds are enantiomers or diastereoisomers. And again, we always want to focus on this idea. We want to draw the skeleton the same way. So you may have to do some rotation. You may have to rotate your bonds. That's okay. Build the model kit, and then we'll take a look at these molecules. And don't be shy to ask questions during this time. We'll spend about 4 to 5 minutes on this problem. So build the model kit. If you need to assign the stereocenters, you can, but try to focus on drawing the molecules the exact same way from the exact same perspective, and then seeing whether the stereocenters are in the same positions or in different positions in terms of three-dimensional shape. And you just need to pick, when you're building the model, make sure it matches 1 for 1 with the drawing. And if you need a starting point, you can just start with the structure on the left. And just build a model of exactly what you see. You don't have to do any rotation at the start. Just draw exactly what you see. and then we'll come together to discuss in about 3 to 4 minutes. I want to give everyone time to build the models, formulate their own opinions, and that way we can have an interesting discussion. And if there are any questions during this time, please don't hesitate to ask. This really is a lot of the lectures are set up in a way where we're doing a lot of guided problem solving. So don't be shy if you have questions on a specific aspect of the problem, or if you have a proposed solution, whether the molecules are enantiomers or diastereomers, don't be shy to share. And don't be shy to type your response to this question in the chat. We're going to be talking about it in a few more minutes. And I encourage you to build a model of both of the structures and then try comparing them. Or you can try to rotate one of the structures to get the other structure. Both methods will work. Anyone have any questions so far? Anyone have any questions so far? And if you have a proposed solution, don't be shy to type it in the chat. I know for such a one-word answer question, it's a lot of work, but these are very similar to questions that you'd see on the exam. Would anyone like to propose a solution for this problem? Would anyone like to propose a solution before we get started with our discussion? Enantiomers or Diastereoisomers? Or would everyone like a little bit more time on this problem? Could you type in the chat just to give me a sense of where everyone's at? Okay, we have someone who's proposing enantiomers. I see a lot of responses for enantiomers. So let's take a look. Okay, so here is the structure on the left. Don't worry about this giant alkyl chain for right now. Let's just focus on our methyl group and our two methyl groups. So if we think about it from the perspective of our camera, are the methyl groups, these two groups that are in my back hand, are they pointing towards or away from the page? Are they pointing towards or away from the page? Away. Okay, so both our methyl groups have the dash notation. We're good to go in that respect. Okay, now I'm going to put the structure on the left down, okay? The structure on the left is being put down. And we have, now I'm raising up the structure on the right, okay? So from our perspective, from our perspective, let me get this set up just right. Okay, so notice how the alkyl chain, notice how our alkyl chain, oops, one moment. Here we go. Okay, so notice how our alkyl chain is depicted the exact same way as our drawing. So we have this 5-carbon alkyl chain, and now what I'd like you to tell me is our methyl group, let me take the hydrogen off as it's a little distracting. Is our methyl group pointing towards or away from the page in this structure? Is this methyl group pointing towards us or away from us? Towards us, okay, so we've checked that box. Okay, does everyone notice how our 5 alkyl group carbons look exactly like the drawing? They're arranged in the exact same way as the drawing. Does everyone see that? Does everyone see that W shape? Okay, now what I want you to focus on next, looking at this big bulky alkyl chain, if we compare it to the hydrogen, is this big bulky alkyl chain in the front or in the back? Is this big bulky alkyl chain in the front or in the back? It's in the back. Okay. So our goal is to get this alkyl chain in this position. Okay? So we want this alkyl chain to be rotated so it's in the position of the methyl group. So all we're going to do is we're going to take our carbon-carbon bond and we're going to twist it until our alkyl chain, this long alkyl chain, is now flat in the plane of the page, okay? And now what we're going to do, now that we've subjected this molecule to rotation, you're going to tell me, what do you see? You're going to tell me, what do you see? So, is our methyl group on the left? Is this methyl group that we said was originally pointing out of the page, is it still pointing out of the page? Is it still pointing towards us? Is this first methyl group? Yes. What about our second methyl group now? Is our second methyl group pointing towards us? Yes. Okay. So we're going to draw exactly what we see in our model. Draw what you see. So we have a long alkyl chain. One of our methyls is pointing out of the page. Our second methyl is also pointing out of the page. One, two, three, four, five. 1, 2, 3, 4, 5. Okay, so now we can do a direct comparison between our two structures. So if we compare these two structures side by side, is the configuration at our chiral centers the same at every center, or are they flipped at every single chiral center? Are these diastereomers or enantiomers? Looking at these structures drawn in the same view. Yep, the stereochemistry is flipped. Ergo, we call that, if the stereochemistry is the opposite at every stereocenter, we call them enantiomers. And again, the only reason why we're able to do this comparison, we need to make sure we draw the skeleton the same way. And the way that we did that, just as a refresher. So originally we had this skeleton here with our alkyl group in the back. In order to get the alkyl group in the plane of the page, like just flat in the plane of the page, we took this carbon-carbon bond and we rotated it. We rotated it, so now our alkyl group was flat. And from there, we noticed our methyl group was pointing out towards us. So we adjusted our methyl group to a wedge when we draw our molecule with our alkyl groups completely in the plane of the page. Does that make sense to everyone? Does everyone see what I did with the model? All we did was rotate a carbon-carbon bond. Does that make sense? And now when we've drawn our structures the same, we can compare the stereocenters and see that we've just flipped the configuration at every stereocenter. Any questions? Is this making sense so far? Is everyone comfortable with this idea? Can I get some feedback in the chat? Don't be shy if you have questions. If not, we'll be doing more practice. This is a skill I want you to be able to develop. Okay, I'd like you to take a look now at the following pairs of compounds, and I'd like you to tell me whether the pair are enantiomers or diastereoisomers, or diastereomers for short. And I'll give everyone about 4 minutes to work on this one, and then we'll come together as a group to discuss. In the meantime, I'm going to be carefully making a model kit. So if you hear some background sound, oh wow, someone already proposed diastereoisomers. Let's take a moment, let's have a few more responses, and then we'll discuss this as a group. But it's good, people are getting faster at solving these. This is an important fundamental skill, so it's good that everyone's enthusiastic. Okay, I see a lot of people typing diastereoisomers. So let's make a model. Let's make a model. And remember, you want to make sure your alkyl chain exactly matches, like you're taking a picture, whatever structure is drawn. You don't want to have any variations create issues. Because remember, as we've established previously, rotation is a killer for these types of problems. If you rotate your molecule, suddenly you may be talking about an entirely new diastereomer. So just be really careful whenever you rotate your molecule. You don't want to accidentally flip a stereocenter and then spend 5 minutes wondering what's going on. Okay, so we're almost done. I'm almost done making the model, almost done. Just always checking meticulously to make sure I haven't misassigned any stereocenters. Okay, so here we go. So here is the structure on the left. So here is the structure on the left. Okay, as we can clearly see, both our alcohol and our chlorine in blue are pointing towards us. Does everyone agree on that? Does everyone agree on that? Additionally, does everyone notice how our alkyl chain, our carbons, look exactly identical to the arrangement of our carbons in the structure on the left? They're zigzagging, facing to the right. Okay, perfect. Now I'm going to show you the opposite I'm going to show you the structure on the right. And we're just going to check to make sure that I didn't make a mistake. Okay, so here's the structure on the right. Here's the structure on the right. So are the alcohol and methyl group pointing out of the page towards us? Are the alcohol and methyl group pointing out of the page towards us? Yes. Okay. So now we want our methyl group to be in the same spot as the chlorine. We want all of our carbons to be flat in the plane of the page. So all we're going to do is we're going to take this molecule and we're going to rotate it until our methyl group is in the plane of the page. Now what I want you to tell me is the chlorine pointing out of the page or into the page? Out or in? In. Okay. So then we draw it with a wedge or dash. How would we draw our chlorine? Would we draw it with a wedge or a dash? Dash. Exactly right. Okay, so by direct comparison now. So by direct comparison, whoops. If we compare these two structures, we can see that only one stereocenter is flipped, and as a result, these two molecules are diastereomers. Does that make sense to everyone? Is everyone comfortable with the idea of rotating molecules and then comparing this configuration at each center? Okay. So let's do a few more examples. And before we tackle the next set of examples, let's talk about a potential wrench in the works here. So symmetry and chirality. So Miso compounds are best defined as a compound with a plane of symmetry. Miso compounds are achiral. So a plane of symmetry is a plane where the atoms on both sides of the plane are identical mirror images. Oh, so for the previous question, the CO was towards us in the structure on the left, but we then made a model of the structure on the right. So this is model 1, and this is model 2. And essentially what we did is we rotated model 2 to match model 1. So we started off with the following model 2. So this is our depiction of the structure on the right, and we rotated our carbon-carbon bond, so our structural skeletons were drawn in the same manner. The skeletons are identical. We then look at our chlorine and we assign whether it's pointing out of the page or into the page. We see it's pointing into the page. So if we compare it to our original structure, which I'll show you a model kit of right now, if we compare it to our original structure on the left, by comparison, we see very clearly that the chlorine in our structure on the left was pointing out of the page. Because this stereocenter was flipped, we conclude that we have diastereomers. Does that make sense? Or is there a follow-up question I can address based on that? Did that clarify? If you have a follow-up question, don't be shy to type it into chat and I'll address it. One moment. Okay. So as we were discussing Miso compounds, these are compounds with a plane of symmetry. So it's a plane where atoms of both sides of the plane are identical mirror images. So for example, for this following species, such as tartaric acid, we can draw a clear dividing line down the center of our molecule. And as we see, we have identical substituents within the identical positions on both sides of our plane of symmetry. We've actually seen examples of planes of symmetry before, but let's expand upon this a little bit. So Miso compounds are not enantiomers. Miso compounds are identical compounds. They are not separate enantiomers. And to really showcase this, it's best seen with a model kit. And I know it may seem like the model kit is a solution to every single one of the problems that we're encountering, but it is useful. So let's start, and this is always a really cool demonstration. So first things first, I'm going to make a model of the structure on the left. Can everyone verify to me that these OHs are pointing towards us? Does everyone agree the OHs are pointing towards us? Now, from this perspective, can everyone see how if I divide my molecule in half with my hand, both of the halves are identical? Does everyone see that when I divide my molecule in half with my hand? If I draw my plane of symmetry right down the middle, we split it physically with our hand, that both of the halves are identical? Okay, now I'm going to take this model away and I'm going to show you a model now of the structure on the right. Can we both verify that these alcohols are now pointing away from us? Does everyone notice how the alcohols are pointing away from us? Okay. Now, I want you to watch really closely what I did to go between these two enantiomers. And this explains why these species are not enantiomers. They're the same compound. All I had to do was rotate my molecule. All I had to do was rotate my molecule 180 degrees. So then, are these two depictions different molecules? Are they truly different 3D arrangements of atoms? Are these two depictions describing different molecules? No. These two depictions are describing the same molecule. Same molecule, just rotated. Does that make sense to everyone? Does everyone see how, because there's a plane of symmetry, we can invert our molecule, and if the plane of symmetry is preserved after inversion, then we have the unidentical molecule. Okay, so Miso compounds are identical compounds. They're not enantiomers. If you can generate your enantiomer in quotes via rotation, then it's not a genuine enantiomer. Does that make sense to everyone? Is everyone comfortable with this idea of Miso compounds? Okay, so let's take a look. And with this idea in mind, I'd like you to apply this, and I'd like you to draw all the stereoisomers for the following compound. And I'd like you to label any Miso compounds. And I'd like you to tell me how many unique stereoisomers we can possibly generate. So take a moment and remember that the plane of symmetry requires the substituents to have the same stereochemistry on both sides of the plane of symmetry. So take a few moments, work on drawing a few molecules, and then we'll come together to discuss in a few minutes. And if you need help checking whether you have enantiomers, diastereomers, or Miso compounds, don't be shy to make a model. And if you can, and if you'd like, you can message me your answer for how many unique non-identical stereoisomers we have for the following molecule. And just a hint, the 2 to the n formula is the maximum. The actual amount you observe depends on whether or not you have Miso compounds, which are identical. So let's take about 3 to 4 minutes to work through this problem, and then we'll come together to discuss. Anyone have any questions so far? And don't be shy once you have a reasonable answer for the number of unique stereoisomers to send a message, just so that way we can have a nice discussion and talk about all the proposed answers. Once you have the maximum number, try drawing out the stereoisomers and seeing if you have any meso compounds, any compounds with planes of symmetry. That's my hint for this problem. We'll try drawing them out and see. And we'll discuss in about 2 more minutes. Anyone have any other proposals for the number of unique stereoisomers? So let's talk about this. So first and foremost, we have 2 chiral centers. So following our 2 to the n rule, 2 to the second would give us a maximum of 4 stereoisomers. So I'm going to use our square method. So I'm going to draw first and foremost just any arrangement. So I'm going to draw up, up arbitrarily. Now, if I wanted to draw an enantiomer, so if I wanted to draw an enantiomer, we just invert all of our stereocenters. So we get the down, down configuration. If we want to draw a diastereoisomer or diastereomer, all we would do is we'd pick one of our stereocenters and we would invert it. Okay. And then finally, if we wanted to draw an enantiomer, we would invert both of our stereocenters. Okay, I'm going to put some numbers next to my structures. I'm going to put some numbers next to my structures. 1, 2, 3, 4. So which structures have a plane of symmetry? Which structures have a plane of symmetry? Which structures have a dividing line that if you cut it through your molecule will lead to the identical substituents, both in terms of the type of substituent and the stereochemistry of the substituent. And I see a lot of people typing 1 and 2, and that's exactly right. So let's take a look at structure number 1. So if we cut this molecule in half, our substituents are the groups on both sides of this plane of symmetry identical? Does this molecule have a plane of symmetry? Yes. So there is a plane of symmetry. So here's a model of the up 1,3-dimethyl cyclohexane. So if we cut it down the middle, our substituents are exactly the same down the middle. Now, to get the down-down stereoisomer, all I have to do is just invert my up. So my question to you is, if I can obtain the down-down enantiomer in quotes via rotation, is it a genuine enantiomer? Are these two molecules the same or different? Are these two molecules the same or different? They're the same. They're exactly the same. They're just the same molecule rotated 180 degrees. So then, in terms of our actually unique molecules, we have 3 and 4 as unique molecules, and then 1 of this Miso compound. So these two compounds are Miso to each other. They're identical. So we have a total of 3 unique stereoisomers. Plus 1 Miso. And we don't really include the Miso because it's identical to one of our stereoisomers. Does that make sense to everyone? Does everyone get why there are only 3 unique stereoisomers? Oh, for those who thought 3 and 4 would be Miso, let's take a look. Let's take a look. Things are best proved via experimentation. So let's take a look at number 3. So if we divide this molecule straight down the middle, are the substituents the same or different on both sides of our dividing line? Are they the same or different? In terms of position, are methyl groups in the same relative position? Different, right? So in order for a compound to needs to be Miso, when you divide your molecule using your plane of symmetry, the molecules need to be the same substituents in the same relative positions. So there is no plane of symmetry for molecules 3 and 4, and that's why they aren't Miso. Does that make sense? Perfect. So let's take a moment and let's have you do a problem now. We'll spend about 4 minutes working through this problem, and I'd like you to draw all stereoisomers for the following compound. And please make sure to label any Miso compounds. So I'll give everyone about 4 to 5 minutes to work on this, and I'd like you to tell me how many total stereoisomers can we draw? And once you have a reasonable solution, don't be shy to message me via chat, and I'll be more than happy to discuss your proposed solution and provide feedback. And we'll come together to discuss in about 3 more minutes. It depends. It depends on how you're drawing your molecule. So to answer your question, Christine, for example, for stereoisomer 1, if our methyls have a wedge, the hydrogens would have a dash. When you're just drawing stereoisomers, you can assign whether the hydrogens have a wedge or a dash. You just need to make sure that for each stereoisomer you draw, it's a unique stereoisomer in the event there could be Miso compounds. Does that make sense? Perfect. And we'll discuss in about 1.5 minutes more. And don't be shy to message in the chat the proposed total number of stereoisomers that are unique. Would anyone like to propose in chat the number of unique stereoisomers that we can draw for this compound? See a lot of people typing 3, so let's go through that and discuss. So first things first, I'm going to start off with the up. Okay. Then if I wanted to draw a quote unquote enantiomer, I would just invert the configuration at every chiral center. If I wanted to draw a diastereomer, all I'd have to do is pick a stereo center and invert it. And if I wanted to draw an enantiomer, I just invert both of my stereo centers. So I'm going to put some numbers next to my compounds. So 1, 2, 3, 4. Are there any compounds that are identical? Or is there a compound that represents a meso compound? Which compound is meso, or more specifically, which pair of compounds are meso? Yep, exactly right. 1 and 2 are meso. So here's a model of structure 1. You can cut it straight down the middle. and both halves are perfectly identical in stereochemistry and substituent type. Perfect. So then we only really have a total of 3 unique stereoisomers. Okay, so as we've reached the end of our class period, we'll resume next class session.